And at standard temperature and pressure, room temperature, normal pressure, which would be 760 millimeters of mercury or 14.7 psi at sea level, and so on and so forth, we're going to be assuming for a lot of the problems that we're working with that, to simplify things, that the conditions meet that criteria. Now, it may be true that in real life, it might be a warm room and it might be 90 degrees instead of 70 degrees. It might be, we might be doing work in Denver, which is 5,000 feet, a mile above sea level, and the density of the air is somewhat different, right? We're going to cross that bridge when we come to it, but a lot of these problems are going to assume standard temperature and pressure for the moment. Problem with this, the additional problem with this is that when we talk about standard temperature and pressure, temperature could be Celsius, could be Fahrenheit. Density could be English units, could be metric units, and so on and so forth. So it's conversion between recognizing which units you're working in, and conversion in units is going to be an important part of this course. It's going to be a really annoying important part of this course. We talked about last week that air is basically nitrogen and oxygen and a whole lot of trace gases, including, most notably for a lot of the stuff we're interested in, moisture, because moisture can cause its own issues, especially when we get to indoor air quality. And carbon dioxide, but we're not doing a course on global warming, so we ain't going to be too concerned about that either. Anybody know anything about the satellite that may have been, I don't know if it went up or not, that may have been launched today? SpaceX, you know what SpaceX is? SpaceX is a private corporation that launches rockets. It's owned by a guy by the name of Elon Musk. Anybody know that name? He made all his money in PayPal, and he decided to go into these other technologies. He's kind of like almost like a Steve Jobs type of guy, except he's involved in a lot of different technologies. He started 3 companies after he sold his share in PayPal. One of them is a solar energy company. They don't really make solar panels. They install them and basically do free installations, and then they charge for the energy that's generated from them, which is a unique business model. He started Tesla, which is an electric car company, and they make I don't know, you can only call it a spectacular electric car, really high-end sports car. It's less than $100,000, which a lot of high-end sports cars cost more than that these days. But it's really a very high-performing sports car. It was named Car of the Year by I forget which magazine does that last year. I think it's the first electric car ever that won that award. But at any rate, very interesting guy. Today, his company SpaceX, which launches rockets into space and has a contract with NASA. You probably have seen it on TV every once in a while. They managed to make the first successful launch of a private rocket carrying a payload to the International Space Station. We have no way to get anything to the International Space Station, including personnel or equipment, now that the shuttle program has ended. Our astronauts go to Russia and use the Soyuz capsule to get up to the space station and come back down. Meanwhile, we get equipment up there by using private rocket launches. And his rocket has gotten a contract for, I think, 50 or 100 missions or something like that, after they managed to come up with a couple of successful missions where they were able to demonstrate that they could do this. Their Falcon 9 rocket right now is on Cape Canaveral. That either launched or it didn't launch today. I'm not sure. The weather conditions are kind of iffy. And it has a number of payloads, a couple of communication satellites, and so on and so forth. And it has a satellite that I'm a little older than you guys. About 20 years ago, got named the Goresat. Anybody recall that? Mean anything to you? Al Gore, vice president. Traditionally, the vice president has responsibility for some management issues or public relations issues with NASA. You might have seen old movies like The Right Stuff and stuff like that, where Lyndon Johnson was involved with the astronauts and their wives and the whole program and so on and so forth in the background. Al Gore, when he was vice president, was similarly involved. And he had an idea because he was kind of ahead of the curve environmentally. He had an idea that in order to increase people's perception about how small a planet this is and how we can have an effect on the planet globally, he proposed putting a satellite up that would orbit would be located a million miles from Earth, stationary, staying the same, would actually move because the Earth is turning and moving, would be basically stationary over the sunlit side of the Earth, 24 hours a day, and beam back pictures of the Earth from a million miles away. So you could actually, that picture you see traditionally of the moon, of the Earth in the background from the moon, you could actually see that. You go on the internet and see that anytime you wanted to. Well, they actually built a satellite for $95 million or $100 million. But it got buried in Congress. The Republicans called it Goresat. They said they wanted no part of it. They held up for funding for launching it, and even beyond that, the shuttle program had a couple of disasters, so they canceled a lot of flights and they were backed up with a lot of missions. So wound up never being launched, and it was been in mothballs, basically in a closet somewhere, a clean room or a closet at NASA for the last 15 years. Well, it turns out that we have two weather satellites that are vital to predicting for long-term predictions of severe weather storms that are past their expected life and could fail at any time. So they desperately need a replacement for them. But for one reason or other, the satellite, the end of the shuttle program or something like that, they weren't able to launch any more satellites to replace them. And they realized, well, we have this one sitting here that'll do exactly that. It'll take a picture of the Earth and we'll be able to see these weather systems forming. So it's on that rocket right now, getting ready to launch. So we may actually be able to see that. The other exciting thing about it is that part of their methodology is that they want to recover these spent boosters so they can reuse them, make it more economical. And they tried this. They actually have this thing designed to land after it's gone into space and released this satellite, for this booster to come back and land on a platform out at sea. They tried this once already. It actually hit the platform, but it hit it too fast and it destroyed the booster. I think they're going to try it again on this one. So we might actually see a double whammy of this thing going up and this thing actually re-landing on a platform. So it'll be interesting to see that happen. So I've wasted a lot of time here. So let's move on. But at any rate, that's going on right now. So it's pretty interesting. Standard temperature and pressure. Okay, so now one of the primary formulas that we're interested in is something we call the ideal gas law. This is kind of a conglomeration of a lot of different things we know about gases, from Avogadro to Boyle to you name it, a whole bunch of stuff. Basically, it says pressure times volume is equal to these quantities. N times R times T. N, P is pressure, V is volume, N is the number of moles, the quantity of a gas, the mass of a gas or quantity of a gas. Moles is the molecular weight in grams. So if you're talking about 1 mole of hydrogen, you're talking about 2 grams of hydrogen, right? H2. If you're talking about benzene is C6H6. So that's 12 times 6 is 92, 60, 72 plus 6 is 78. I presume I got that right. I'm not sure. So 78 grams of benzene is 1 mole of benzene. Both of those at standard temperature and pressure, 2 grams of hydrogen, 1 mole, and 78 grams of benzene take up the same amount of space. They have the same number of molecules, 6 times 10 to the 23rd molecules. They take up the same amount of space. Both of them take up 22.4 liters. I'm having a senior moment. 22.4 liters of space, right? At standard pressure and standard temperature. That's the volume. Okay, so now if we have any given gas, like a gas, a certain amount of that gas, a mole, 5 moles, 2 moles, or 3, then all the rest of these numbers in this formula will work for that gas. R is a gas constant. It's a number that takes care of all of the other variables that might be in here, including correcting for the various measurements that we're using, pounds per square inch of so on and so forth, right? To make up for the volume, and whether it's in square inches, in cubic inches or cubic liters or cubic meters, and so on and so forth. So what do we see here? N and R are fixed by the amount of gas and this constant that's universal to all gases. Okay, PV and T can vary, right? So how do they vary? Well, if you increase the temperature, then either the pressure or the volume have to increase too, because there's one side of the equation increases, the other side's got to increase. Could be that if the volume is fixed, then the pressure has to increase. If the pressure is fixed, then the volume has to increase. There's a relationship between these three things: pressure, temperature, and volume. That's defined by this formula. And we're going to take advantage of that. Okay, says related to pressure and temperature to perfect graph. Okay, pressure is equal to the density times R times T. What's the density? Density is really just the volume, is just the mass per unit volume. So V is in that formula. So this is another form of that formula. It's just been moved around a little bit. Now, the density of air at standard temperature and pressure has a certain quantity. That density is determined by the pressure that it's under. Okay, now normally we're sitting here in air, and it doesn't seem like air in this space is under pressure because we live in this environment, and this pressure is static pressure. What do we remember about static pressure? It's exerted in all directions. It's in our lungs. It's going in the same. It's pushing out our lungs. It's pushing in on our bodies, and so on and so forth. So to us, our perception of it is that we're in zero pressure. And in fact, if we had a pressure gauge, what we would call, like so many psi G or gauge would be zero. Gauge would read zero. But in reality, we're under 14.7 pounds per square inch. That pressure is generated by the weight of air above our heads. Okay. Now, if the air is warm, the air is lighter, right? So the pressure is lower. The air is pushed together less, so its density is less. There's less. It takes up more space for the same volume, same mass of air. It takes up less space because it's under less pressure, and it can expand a little bit. So the density changes based on what the atmospheric pressure is. So the density of air is different here than it is on Mount Everest. And we're going to use a formula. We're not going to recalculate this every time. It's going to be damn inconvenient to do this. So we're going to say that the actual density, the density where we happen to be when the barometric pressure is very low or high, in other words, when there's warm air or cold air on us, cold air is very heavy, so it tends to barometric pressure tends to be higher. On those days, if we really wanted to be accurate, the actual density is going to be equal to the density at standard temperature pressure times some differential factor that we're going to multiply it by. And that differential factor is going to be based on temperature and some other factors. We'll actually look at that in a second. So rather than calculate this, by using this original formula every time we want to do it, we're going to use a table to actually do it for us. And we have actually exercises to do that with later on. Another variable of this formula, another variance of this formula is to take, remember, pressure and volume were on one side, temperature were on the other side. Well, you can kind of put them both on the same side and say pressure times volume over the temperature of a quantity of gas is going to be equal to, if you change any one of those factors, is going to be equal to the pressure, new pressure times the new volume times the new temperature. So if you increase the temperature if you change the temperature from temperature 1 to temperature 2, it's going to affect the pressure and the volume of that gas. And we can use this formula very directly to determine, well, if in state 1, if we start out with standard temperature and pressure, and we have 1 liter of air at atmospheric pressure, 14.7 pounds, and it happens to be 20 degrees centigrade. And now we increase that temperature to 40 degrees. Well, we know it's going to affect the top half of that formula. And we can actually use this equation to calculate how it affects the pressure or the volume. And we have an example of that we're going to play with. Okay, so I'm not going to actually run it through here. We'll do it when we get to our examples. Now, air movement is caused by differential pressures. The reason why air moves through a duct is because it's moving from an area where the pressure is higher to a place where the pressure is lower. When heat moves from a place where the temperature is higher to a place where the temperature is lower, right? Take heat away from something. So just like that, whenever we see a lower pressure than an adjoining area, we know air is going to move in that direction, especially when we're working with ducts. Now, in a duct, there's two kinds of pressures that we're concerned with. One of them is static pressure. And static pressure is the pressure that is present all the time, acts in all directions. If there's no fan operating in the duct, the static pressure is 14.7, the absolute static pressure is 14.7 pounds absolute, or 0 psi absolute. Pressures in ducts are not much different than standard pressures, right? Because we really, in a large duct or something like that, it's hard to build up a lot of pressure. It's not like we're filling a cylinder under hundreds or thousands of pounds of pressure like we might fill a cylinder with nitrogen or carbon dioxide or something like that. So the pressure differences between one side of a fan and another side of a fan are not that great. And we need an easy way to measure them. So the easy way that we use to measure them is, instead of using PSI or some other metric measurement, is we say, well, that pressure, how much is that difference in pressure? How can I relate that to the weight of a column of water? So you guys have seen these columns. Unfortunately, didn't bring my graphics tablet with me, so I can't draw. So I'm going to have to hope that we have something here that's going to illustrate that for you. Here's a duct, right? So in this duct, the furthest to the right, the tube that's furthest to the right, it's a simple U-tube, right? And there's a fan in there. There's a fan in this duct. The fan's blowing air to the right. So everything that's on this side of the fan is under a negative pressure relative to the other side of the fan, right? This is the low pressure side. The fan's pushing stuff, so it's sucking stuff through here. There's the low pressure side. The air is going to go towards the higher pressure, the other side of the fan. Okay, so now the furthest to the right, this tube, could be a simple plastic tube. Now, if that fan is not running, the pressure on the side of that tube, which is open to the side of the duct, is 14.7 pounds, the same static pressure that's going on all over the world. On the other side, it's also 14.7 pounds. So that tube levels itself out. The height of that water in that tube is the same height, no matter what's happening in the rest of the world, right? When that fan goes on, the downstream side of that, the upstream side of this fan becomes negative. The pressure becomes negative. So you can imagine that's going to start sucking. It's going to suck air through the duct, but it's also going to pull with equal vigor air up through that tube. Since there's water in that tube, it's going to draw that water up. Now, if there were enough suction there, it would suck the water right out of the tube. But most duct systems and fans don't really generate that big a difference in pressure. So what will happen is it'll pull that water up until the difference in the heights of the column of that water, that weight of water that's different between one side and the other, is equivalent to the suction on that side of the duct. And we call that inches of water of vacuum or of pressure. So the static pressure here is -1 inch of water. Okay, we could have called that PSI. We could have called it a million other things. This is a really convenient way for us to describe this. Okay, so static pressure acts in all directions. You have static pressure in a balloon and you blow it up, right? In every part of it, the pressure is the same, and it's acting in every direction possible. Oh, thank you.
I'm going to interrupt.
Okay,
That's
that's good. Oh, good. Terrific. Oh, good. Thank you. Okay. So now the other kind of pressure that we can get, if you look at the one to the far left, right, that's called velocity. But I'm not. Let me stop right here. Let's look at the middle one first. Now we take that tube, instead of putting it up against the side of the duct, we run it in the duct and we point it in the direction of the airflow. So now we get air blowing into that duct. We get something called pressure that's caused by the velocity or movement of the air, velocity pressure. Now, the thing is that, that's not just pressure from the movement of the air. We just said static pressure is acting there all the time anyway. So that pressure is really both velocity pressure and static pressure added together. That makes sense to you guys? Anybody uncomfortable with that? That's both pressures, because you always have static pressure in that. Whether you point, even if you pointed it downstream, you would still have static pressure, right? Pointed upstream, you have static. If you pointed downstream, you would have only static pressure. If you pointed upstream, you would have the static pressure plus the pressure from the velocity of air. Okay, so that is static pressure and velocity pressure added together. That's called total pressure. So if you wanted to know only what the pressure was from the movement of the air in this duct, you would have to take what you see there from that total pressure and subtract the static pressure from it. Okay, so the total pressure is 3 inches, right? The static pressure is 1 inch. What do you think the velocity pressure is? I'm sorry, the total pressure is 0.3 inches. The static pressure is 1 inch. What do you think the velocity pressure is? The difference between the two, right? Things are a little complicated here, right? The velocity pressure is 0.7 inches, right? You're uncomfortable with that?
No, I'm thinking minus. Instead of 0.4.
Yeah, well, you want to know something? It is minus, because the velocity pressure, the velocity, total pressure, negative pressure, hang on a second. No, notice that it can be negative, and we're going to talk about that in a second. Velocity, that can be negative. Well, the velocity pressure is going to be positive because the air is moving into it. That's always going to be a positive number. But the total pressure can be negative. It's possible for the total pressure to be negative. Let's take a look back here. Okay, here's a duct, and we're looking upstream and downstream on this duct. The velocity pressure is the same downstream and upstream, because it's only the pressure that's caused by the air blowing into that tube. And since the duct's the same size, it's going the same speed, it's going to be the same pressure. So the velocity pressure downstream of the fan and upstream of the fan are not only the same, they're both positive. Okay, everybody comfortable with that so far? Okay, what about the static pressure? The static pressure upstream before the fan is negative because it's under a suction. After, it's positive, right? Because it's the fan is pushing air through. So imagine if we put that tube there, it would go the opposite direction. Air would push down on the tube instead of suck up on the tube. Next week, not next week, we're not going to be here we probably won't be here together next week. The following week, we're going to go down to the lab for half an hour. We're going to set up a fan and a duct, and we're going to do this so we actually see this work. Okay, so the static pressure on one side is negative, on the other side is positive. Well, what about the total pressure? What do you think might happen there? Well, in general, the total pressure upstream is going to be negative. Total pressure downstream is going to be positive, or at least relative to each other, because that's what makes the whole thing go, right? Pressure's got to be lower on one side than on the other side. That's what makes it actually work. Okay, so don't get too worried about that yet. We'll work through this a million times. The next problem we have is that there's friction on the sides of these ducts. It's not a perfect environment. If you looked at the right side of the movement of air in this diagram, you might call that something called laminar flow. The flow is perfectly even through this ductwork. As far as ducts are concerned, this never happens. The air would have to move so slowly that for this to happen, that in effect, we really never deal with laminar flow. On the left-hand side, you see what reality is. What's happening is that the air is being affected by friction on the sides of the duct. So it's moving more slowly. There may be eddy currents building up in there that change the direction and interfere with the movement of air. And in fact, the velocity of the air moving through the duct is fastest through the middle and slowest at the ends. Okay, and what does that tell you about the velocity pressure? It's highest in the middle and lowest at the sides, right? So velocity pressure and velocity are directly related to each other. Velocity pressure is caused by how fast the air is moving. Faster the air is moving, the higher the velocity pressure. Okay, we have a couple of formulas, one in US units, one in metric units, on how to calculate this. And this is a simplification of what the real measurements are of this, but the velocity of the air is equal to 4,005 times the square root of the velocity pressure over a density correction factor. That D is the density correction factor. Now, if this is standard pressure and temperature, that D is 1. So it's just the square root of the correct for it. Then if D is 0.8, like in other words, the air is only 8/10 the density of air at standard temperature and pressure, like where we're at the base camp on the Himalayas or something like that, where we have a duct. Not likely to have a duct on base camp in the Himalayas, I guess. But if you had one, then that density might be 8/10 of what it is at sea level. And we might be dealing with a very different situation for the effect of this velocity. So that's how we would use the calculation. We divide by 0.8. We're going to see a table that helps us with that in a few moments. Okay, and if you don't know if you don't know the correction factor, but you do know the density, you can use the second formula to calculate it from the density. This may come up because we might give you a problem or something like that where you would use it. Now you have two formulas. So if you give you the density, you can use one. If you give you the correction factor, density correction factor, you can use the other. Again, total pressure, static pressure versus velocity pressure. Velocity pressure is equal to total pressure minus the static pressure. Use it any way you want. Okay, so now talk about air moving through a duct. Q represents the volume of air moving through a duct. That's usually cubic feet per minute or per second. V is the velocity of the air. A is equal to the area, the cross-sectional area of the ductwork. To put it simply, if you have a duct that's 12 inches by a square duct, 12 inches by 12 inches, that's 1 square foot. If air is moving through there at 100 feet per minute, right? That means for every minute, you got 100 cubic feet of air moving through there. 100 feet per minute times 1 square foot is 100 cubic feet per minute. If the area were 2 square feet, 100 feet per minute velocity going through 2 square feet now would be 200 cubic feet per minute. Simple enough, right? Okay, so we're interested in the area, cross-sectional area of the ductwork and the velocity of air going through it. If you know the quantity and you know the area, you can calculate the velocity that the air is moving through it. And we're really interested we need to know volume because we got to design these systems. We need to know how much air, what kind of fan we need, what kind of air movement we got to produce. We need to know velocity because whatever this contaminant is that we're going to deal with and we want to remove, we got to capture it. And we're going to use that by using the velocity of air. Okay, so the units, we can play around with the units. I'm going to try as much as possible stick with US units because that's the way air conditioning mechanics work. That's the way most industry works in the United States. That's the way air conditioning mechanics works. Occasionally, we may throw in some stuff where you got to work with metric units just so you're prepared for it. But most of the time, I'm going to use US units. What volume of air is being drawn into a laboratory hood opening measuring 12 inches by 24 inches if the average face velocity is 200 feet per minute? Hazard a guess? What's the square foot of the air? What's the area, cross-sectional area of the ductwork? 12 by 24 is, right? First we'll convert it to feet, right? 1 foot by 2 foot. 2 square feet, right? Velocity is 200 feet per minute. How many cubic feet per minute are we moving? 200 times 2, 400 cubic feet per air. Q is equal to the velocity times the cross-sectional area. Just remember that inches, you want to change inches to feet right away, because since we're using feet per minute and the rest of it, we need uniform measurements, right? Okay, there you go. Okay, now here's another duct. Now, not all duct work in a system is going to be the same size. Okay, so for instance, this is circular duct as it happens. Circular duct is a little bit more complicated because we have a formula we have to use to calculate the area. It's not as simple as A times B as it is with a rectangle or a square. It's pi times the diameter squared over 4, or pi r squared, right? So it's another way to look at it, pi r squared, okay, radius squared. So for argument's sake, I'm going to say that V1, right, velocity 1 is 200 feet per minute. Area 1 is 1 square foot, whatever that diameter would have to be. Let's say that area 2 is 4 square feet. What's velocity 2 going to be equal to? A1 was 100 feet per minute, 1 square foot. A2 is 4 square feet. What's V2 going to be? Is it going to slow down or speed up? It's going to slow down, right? And the area is 4 times as much as what we started with. So it was 100 feet per minute. So it's going to be 25 feet per minute, right? And if V1 times A1 is 1 times 100 is 100 cubic feet per minute. V2 is V2 times A2, which is 4 square feet. So V2 times 4. Divide both sides by 4. V is equal to 25. We're going to get on to this a point where I'm really sorry I don't have my graphics tablet with me. But basically, that's what we're going to be. That's one of the simplest. Right now, it's a simple application. We're going to wind up doing much more complicated problems with this as you get used to doing these calculations. One of the other things we're interested in is we're interested in capturing contaminants. Not all of those contaminants are going to be gases. A lot of times those contaminants are going to be particles. Particles have mass. So we have to understand what the properties of these particles is. And most of the dynamics of small particles, this may come up in other courses, is based on the size. In other words, you're not so concerned really about the density of the particle directly, but more you can kind of make assumptions. When you're dealing with small particles, make a lot of assumptions based on the size of the particle without worrying quite as much about what the real density of that particle is. So we're going to use some formulas for calculating. This formula Vs is the settling rate of a particle. D is the diameter in microns of the particle, right? Then we have a constant, 0.0052, and specific gravity, okay. SG is specific gravity, is unitless, water is 1. So if it's an aerosol or something like that, if it's water, then basically we don't multiply it by anything. If it's some other substance that it's denser or lighter than water, then we would use it there. But notice that D, the particle diameter, is squared. Changes in the diameter have a much bigger influence on the settling rate of the particle than the actual density of the particle has, right? Because that property is squared. Okay, and this is just another formula that we're going to be able to apply. But you understand why we're so interested in that particular property, because a lot of times we want to capture these things. A couple of definitions. Capture velocity, we got particles and junk like that in the air we want to capture. The velocity that you need to get that particle and pull it into your exhaust hood is called a capture velocity. Seems pretty obvious. Now, once it's in the ductwork, you don't want it to settle out. You want to get rid of it. Otherwise, you're going to have a lot of that crap build up in your ductwork. You need to maintain a certain transport velocity. Okay, the minimum velocity you need to keep it moving through the ductwork is called the transport velocity. Okay, so some of the issues we're going to wind up with is that turbulence that we were talking about, the friction from the sides of the ductwork, is going to influence these things because we have a fan in this system, but we may have a long run of ductwork. We may have turns in this ductwork. We may have a certain geometry to our hood. We have filters in there and so on and so forth. All these various devices, they increase friction or they slow down the air movement. They affect the air movement. So they all impede. So if we have a long run of ductwork, right? And if we have a short run of ductwork, long run of ductwork, the geometry otherwise is the same fan, same diameter, and so on and so forth. We may not be able to move air as efficiently or quickly. We won't have the same velocity if we have that long run of ductwork because that's a lot of resistance to the movement of the air. Okay, local exhaust ventilation. That's what our business is. That's what you guys right now, you can forget about being MPHs. Right now in this class, you're EOHMS guys, right? Because your business is to make sure that contaminant does not affect the worker. And the way you're going to do that is you're going to capture those contaminants right at the source so they don't get out into the room, so the worker doesn't breathe them, he isn't exposed to them. That's your job. You are no longer an MPH. You can be an MPH in another class. In this class, you're going to be industrial hygienists for a little while. Anyway, we'll be maybe for some sessions we'll be MPH people, but for the most part, we're going to be industrial hygienists here. Okay. Generally, I don't know if this statement's usually true, not always true. Generally, you will design these hoods because the worker's working at a station. He's working here soldering, Android boards, he's in China, he's making iPhones or something like that. He's soldering. He's in another plant and he's grinding parts for cases and stuff like that. He's in another plant and he's working with tanks of solvents for cleaning bumpers that are going to be chrome plated or something like that. He's going to be working at a station, at the same station all the time. Generally, it's a fixed station. The hood is fixed, designed for him to work in that environment and to pull these exhaust gases away from him. That's generally the situation. Occasionally, it's a little bit different. You may have been on jobs where you've seen welders work. Sometimes welding fumes are very, very tiny particles. Now, you see he wears a mask. He may have a respirator and so on and so forth. These fume particles are super tiny, right? So respirators, tiny as a leak or something like that, he's going to breathe this stuff, right? So you may have seen these guys use a rig where they have a device with a filter and an exhaust fan in it, and ductwork, maybe 6 or 8 inch ductwork, goes up to kind of a movable arm, like a robotic, almost like a robotic arm that he can grab and pull. And it's got a exhaust hood on it, a shrouded exhaust hood that he can pull up right to the place where he's welding something and turn that fan on, and it sucks that material away from him. And he can move that into the next room if he's welding pipe in the next room. And he can manipulate that so that if he's got to work on this side, it's pulling the particles away from him. So it's not always true, but generally true that you're working at a fixed location with a fixed hood. Local exhaust ventilation usually provided when overexposure as a hazard may occur. In other words, in industry, if they don't need to spend the money, they're not going to spend the money. So usually you see a hood in a situation where there's a serious chance of exposure, right? If it's a kind of a situation where in our shop they use some dilute acetic acid solution, and it smells kind of like a salad half the time, right? But they don't work in that area very often, and his exposure is probably well below the permissible exposure limit. So they don't have a very they have an informal, they have a small exhaust hood over it, kind of captures stuff as it goes up because it's warm solution. The air rises, captures most of it, and controls the odors and stuff like that. But they don't really have a really good, well-designed hood to capture everything and take it away from them because they think they're basically, based on their measurements, it's well below the permissible exposure limit for that material. But when you may be close, you need to capture all of this material. And if it's a really hazardous material, welding fumes could be, depending on the material, you really need to capture this stuff. So typically the setup is going to be a hood. It's going to be something to take the junk that you capture out of the air. Could be activated charcoal if it's a VOC. It could be a filter device of some kind or another. Could be a scrubber, uses a water spray to scrub the stuff out of the air. Why are you doing that? Because if it ain't any good for the worker, chances it ain't much good for your fan either. And I'm going to hazard a wild guess. Your neighbors aren't going to be in love with the crap either, right? So you have a few issues there. So very frequently between the hood and the fan, there is some sort of cleaning device, some sort of device to remove the contaminant that may be objectionable in the exhaust air. It could be just odors, could be an odor problem or something like that. And then to an exhaust, then it is usually exhausts outdoors. Now, if you're sucking air out of the room and sending it outside, you can't create a vacuum in that room. This is not going to work unless you supply replacement air for that room. Okay, if you don't supply replacement air, that fan's not going to, you're not going to get the air moving as much as you want. Again, typical exhaust ventilation system. Okay, yeah, there's a few pictures, right? This is an axial, that device is a fan. There's a fan actually buried in there. General ventilation fan. The one on the right might be something you might see in a roof of a plant or something like that, just to get dilution ventilation. This branch duct goes off at a 45-degree angle instead of a 95-degree angle because there's less friction involved in moving air through that angle. There's a whole bunch of filters there. I can see one's activated charcoal, one is a pleated, looks like fiberglass filter, and so on. Cyclone dust collector. What that basically does is as you pull air through it, the air goes into and out of a device that spins the air very quickly. So if the particles have some mass, they're going to be thrown to the outside or the inside, collect down at the bottom. Any of you guys, how many of you guys have taken the EOHS lab course? Right? Those guys remember that they use a cyclone on an air sampling device. So they can measure particulate levels, right, that were under a certain size. It basically was a pump, a filter that you pre-weighed, and you would suck air past that filter and then reweigh that filter to see how much of that dust you picked up. Well, they use a cyclone before that filter, and that cyclone, as you pull air through it, would spin the air, and the larger particles would get caught in that cyclone and drop down to the bottom. Only the smaller particles would come through. So you could then use the same system to measure respirable particulates, particles below 4 microns, because that little cyclone was designed that at that flow rate that it would capture all the particles above 4 microns. And that's kind of what it looks like in the beginning. They actually do collect things pretty effectively. Okay, here's some more duct transitions. That's just changes in, say, shape or size. Flexible duct, which is really obnoxious stuff. Blast gate, when we look at our equipment downstairs, that's a kind of a damp or shut off, turn on or shut off flow. They're not really designed for regulating flow as much as a regular damper, kind of like these things you see axially mounted. But it's really intended for turning on and off, but you can use it to regulate flow as well. It's basically, it blocks a duct or blocks some part of the duct to slow the air movement down. We're going to be using that ourselves. Okay, so let me see what we really need to look at here. One last thing. There is a number called the Reynolds number. This is something we can calculate. The Reynolds number is a calculation that indicates to you whether the flow in this system is turbulent or laminar. What did we say about laminar before? Laminar has no eddy currents, it's nice and even, and so on and so forth. You can imagine to have that kind of flow through a duct, you would have to be moving pretty slowly, right? Turbulent flow, the air is mixing up and blowing all over the place, and it's different velocities, it's faster in the middle and slower in the sides, and so on and so forth. That's caused by friction with the sides. It's also caused by bends and transitions and obstructions and screws and nails and everything else, right? So you can actually calculate the Reynolds number. We have some formulas for doing that, but to make a long story short on the Reynolds number, let me give you an example here. Most flow duct for 1,000 cubic feet per minute, cubic feet per minute of air flowing in a 12-inch duct generates a Reynolds number of 130,000. Let's see. A clean room duct that uses very low velocity air, 90 feet per minute, generates a Reynolds number. If you do the calculation, that's above there, that number you see above there, that gives you a Reynolds number of 12,000. What did we say about this? Laminar flow is under 2,000, right? What they define from Reynolds numbers, laminar flow, between 2,000 and 4,000 is kind of in between, right? And above 4,000 is basically you treat it as turbulent flow. So basically, we're never going to run into a system, most likely, that's laminar flow. We're always going to be dealing with turbulent flow. And we can demonstrate that if somebody wants us to, we can demonstrate that with this calculation for Reynolds number, which is based on the diameter, the volume, the density, and so on and so forth, the viscosity of the fluid these are all fluid. By the way, a lot of the stuff that we're saying, that Q equals VA, a lot of this other stuff, this applies to almost any fluid. It applies to water or oil just as much as it applies to air. It's just another kind of fluid. The main difference with air is that air is compressible, where a lot of these other fluids aren't compressible. So in fact, in some ways, that makes them simpler. And these are numbers that represent the roughness or the friction that's generated by different materials. We're not going to really use this chart. We're going to use a different chart that's actually designed for ductwork. Typical local exhaust system ventilation. To give you an idea over here, the fan is down at the end. The static pressure, remember that suction pressure? That's what's driving stuff here. Static pressure is 3 inches, minus 3 inches at the fan. In other words, it's sucking so hard, if we put a hole in there, put a tube up on it, it would support a 3-inch column of water. Okay, well, if you go back if you go back, you have a bend over here. If you go back before the bend, it's down to 2.6 inches. Where'd you lose that suction? You lost it to friction in this duct because of that bend. And then if you go back before the filter, it's 1.6, right? If you follow the duct down and you make a turn over here, now it's down to 1.2. And at the hood, or in this duct, it's 1.2. At the actual hood itself, it's very low because the hood is large relative to the size of the duct. And so what does that tell you? That tells you if you got a large hood, you better be moving air pretty effectively through this ductwork in order to make sure you got some velocity at that hood so you can capture stuff, right? So we'll be doing this stuff. This is a version of a version of this diagram where what they've done is that they've charted what the suction pressure is. Suction pressure, total static pressure drop was over here, was at the fan. This is where it was at the fan, minus 6 inches. And then there's and then before this system, it's negative 4 inches, and so on and so forth. And by the time you get to the hood, it's about 1 inch of suction at the hood. Okay, so this charts the loss of suction pressure going back from the fan to the hood. They just did what they did with numbers here, they did graphically here. That's the only difference here. That's not different numbers, but that's the basic difference. Okay, this situation, where would you think there's more turbulence and more loss of suction pressure? It's going to be at this curved portion, at the squared off portion, right? You got turns, transitions. You want to make them as smooth a transition as possible. Okay, spray painting booth. Yes, you have spray painting booth here. That whole wall against the back there is basically a suction, a hood, and those filters capture the paint dust, so they don't get pushed, they don't get pulled into the system. Now, notice he's on one side of the car. You got to stand on the other side of the car, you're going to get blasted with this stuff. Here's a table saw. As the material gets cut up, it gets thrown up into that exhaust hood. Now it's completely covered, so that horse, as you're pushing it through, that lifts a little bit. The wood actually keeps a seal on it, so you don't need to move that much air because it's captured within that, contained within that hood anyway. Okay, here's a system of vats here, a plating operation. Now usually these vats are heated, right? So what's going to happen is that warm air is going to rise. So they have the hoods up above it. Now, if you're a worker and you're leaning over that ain't helping you very much because it's pulling it right past you. And those hoods are so far up, they're probably not very effective anyway. Okay, how could this be improved? Well, get that hood down over those tanks. for starters, right? There's also, we're going to learn about other kinds of hoods that are used in these kind of systems. If they're not heated, you might be better off with something called a slot hood at the back of these tanks. But we'll talk about that as the semester goes on. Okay, that asks you for questions. I'm not answering questions, so